Did modern food webs exist 540 million years ago? In our last episode, you met early chordates like Pikaia, humble filter feeders that seemed insignificant in the Cambrian, but carried the body plan that would eventually produce all vertebrates. Individual organisms are fascinating, but they don't exist in isolation. They're part of ecosystems, complex networks of interactions determining who lives, who dies, and how energy flows through communities. This episode explores Cambrian ecosystems as functional wholes, food webs, predator-prey dynamics, competition, and the ecological principles still governing life today. You'll discover that modern ecological concepts had their origins in these ancient seas. We assumed ancient meant simple. For decades, scientists imagined the Cambrian as a primitive world. Predators eating prey in straightforward relationships, nothing like the intricate food webs of modern oceans. This assumption was completely wrong. The Cambrian seas were complex from the beginning, operating under the same ecological principles that govern life today. The difference isn't complexity. It's that we're now breaking those principles faster than ecosystems can adapt. And the Cambrian shows us exactly what happens when ecological rules get violated. The first surprise was discovering complete trophic levels already in place. Primary producers, algae and cyanobacteria, converted sunlight into organic matter. Herbivorous creatures grazed on these photosynthesizers. Predators hunted the herbivores, scavengers fed on the dead. Decomposers broke everything down into nutrients that primary producers could use again. This wasn't a simple system learning to be complex. By the time we find Cambrian fossils with preserved gut contents and ecological associations, the full structure already exists. Life didn't gradually build food webs, it exploded into them. The Cambrian wasn't ecology's childhood. It was a fully formed system emerging suddenly, already playing by rules that still apply 500 million years later. Those rules include the 10% law, discovered by studying modern ecosystems but visible in Cambrian fossil distributions. Only about 10% of energy transfers from one trophic level to the next. 100 pounds of algae supports 10 pounds of herbivores, which supports 1 pound of predator. This creates an inevitable pyramid structure. You need massive amounts of primary production to support a small number of apex predators. This is why Anomalocaris is rare in Burgess Shale deposits, while trilobites and other mid-level creatures are common. Physics demands it. An ecosystem with many apex predators and few prey animals would collapse within a generation. The Cambrian already operated under this constraint. Energy flow determines population structure, whether 540 million years ago or today. This explains something that puzzled paleontologists. Why are top predators always rare in the fossil record? It's not preservation bias. Anomalocaris should fossilize as readily as trilobites, both had hard parts. The rarity is real, dictated by thermodynamics. An apex predator must have a hunting territory large enough to contain sufficient prey, which requires sufficient herbivores, which requires sufficient primary production. Calculate backward from Anomalocaris's estimated metabolic needs and body size, and you can predict how many could exist in a given area. The fossil distribution matches the prediction. The Cambrian didn't just have predators, it had predators constrained by the same energetic limits that constrain modern apex predators. Orcas are rare for the same reason Anomalocaris was rare. The rules haven't changed. The predator-prey arms race we discussed earlier had ecosystem-wide consequences. As trilobites evolved thicker shells, predators evolved stronger mouthparts. As predators got better eyes, prey evolved spines and camouflage. This escalation wasn't just between two species, it cascaded through entire communities. Better predators meant herbivores needed better defense, which meant they spent more energy on shells instead of reproduction, which changed population dynamics, which affected primary producers. Every innovation rippled outward. The Cambrian wasn't creatures evolving in isolation. It was an ecological arms race where every change forced responses from multiple species. Modern invasive species cause similar cascades when they disrupt existing relationships. The Cambrian shows us this pattern at the moment it began. Competition drove specialization in ways still visible in the fossil record. Early Cambrian trilobites were generalists. Similar body plans, probably similar diets. But as populations grew and resources became contested, selective pressure favored specialization. Some trilobites evolved for filter feeding, others for scavenging, others for hunting small prey. Their eyes modified for different depths and light levels. Their legs adapted for swimming versus crawling versus digging. By the Middle Cambrian, trilobites had diversified into thousands of species, each occupying a specific ecological niche. This is competitive exclusion in action. Two species competing for identical resources can't coexist indefinitely. One outcompetes the other, or they diverge to exploit different resources. The Cambrian invented this principle. This niche partitioning allowed remarkable diversity in small areas. The Burgess Shale preserves creatures living in close proximity, but exploiting different food sources, depths, substrates, and hunting strategies. Morella filtered particles from water. Wiwaxia grazed on seafloor microbes. Autoya burrowed and ambushed prey. Opabinia probed sediments with its flexible proboscis. Anomalocris hunted in open water. Each species carved out a living without directly competing with the others. Modern coral reefs show similar diversity through similar partitioning, hundreds of species coexisting by specializing. The principle emerged in the Cambrian and never went away. Break it by removing keystone species or collapsing food sources and diversity plummets. We're running that experiment now on a global scale. Some species did more than occupy niches, they created them. These ecosystem engineers fundamentally altered the environment, changing conditions for every other organism. The most important Cambrian engineers were burrowers. Before the Cambrian, seafloors were mostly microbial mats, layered communities of bacteria and algae forming cohesive surfaces. Then creatures started digging. This bioturbation mixed oxygenated water into sediments, broke up microbial mats, recycled nutrients, and created three-dimensional habitat complexity. Burrows became homes for other species. Sediment mixing changed chemistry. The physical structure of seafloor habitats transformed completely. Modern earthworms serve the same function on land. They're ecosystem engineers whose burrowing fundamentally changes soil structure, drainage, and nutrient availability for every plant. Remove them and ecosystems shift dramatically. The ecological consequences of bioturbation were profound. Breaking up microbial mats opened new niches for species that could exploit exposed sediments. Mixing oxygen deeper into seafloors allowed different bacterial communities to thrive, changing nutrient cycling. Burrows provided refuge from predators, creating survival opportunities for vulnerable species. But bioturbation also destabilized sediments, causing underwater avalanches that buried communities, like the mudslide that created the Burgess Shale. Ecosystem engineering is neither purely beneficial nor harmful. It changes conditions, creating winners and losers. The Cambrian shows us that even at the beginning, ecology was about dynamic interactions, not static balance. Stability is an illusion. Ecosystems are constantly being reshaped by the organisms within them. Mapping who ate whom reveals something startling. Cambrian food webs were already complex and interconnected. Trace fossils show predator-prey relationships. Gut contents reveal diets. Functional morphology indicates feeding strategies. When scientists diagram these relationships, they get webs, not chains. Multiple species feeding on multiple prey, with scavengers and decomposers linking everything. Break one strand and stress propagates through the system. Lose a key prey species and predators must switch diets or decline. Lose a predator and prey populations explode, overgrazing resources. Modern ecology calls these trophic cascades. The Cambrian already had them. The complexity wasn't building toward something. It was there from the start. This complexity depended on nutrient cycling remaining functional. In modern oceans, dead organisms sink and decompose. Nutrients return to surface waters through upwelling, supporting primary production. Remove decomposers or disrupt circulation, and the cycle breaks. The Cambrian operated under identical constraints. We see evidence in fossils of scavengers, creatures specialized for eating carrion, and in geochemical signatures showing active nutrient recycling. Death fed life. Waste became food. Everything was connected in closed loops. This is why ecosystem collapse is so catastrophic. It's not just losing species. It's breaking the fundamental cycles that support all life. The Cambrian established these cycles. They've operated continuously for 540 million years. We're now disrupting them faster than any natural perturbation in that entire span. When nutrient cycles broke in the Cambrian, the results were catastrophic. Anoxic events, periods of low oxygen, killed massive numbers of organisms. With so many bodies decaying simultaneously, oxygen got depleted further, creating dead zones where nothing could survive. These events show up in the rock record as black shales. layers rich in organic carbon that never decomposed because no oxygen was available for decomposers to use. Recovery took thousands to millions of years as ecosystems slowly rebuilt from surviving populations. The species that went extinct stayed extinct. The ones that survived often filled different niches than before. The ecosystem that emerged wasn't a restoration of what existed before. It was something new, built from whatever pieces remained. The timescale of recovery is the terrifying part. After severe disturbances, Cambrian ecosystems took millions of years to rebuild comparable diversity and complexity. Not thousands of years, millions. Individual species might recover faster. Populations can rebound in generations if conditions allow. But ecosystem-level complexity, the intricate web of interactions, the specialized niches, the nutrient cycling, the full trophic structure, that takes geological time to reconstruct. This is why mass extinctions leave such clear boundaries in the fossil record. The world before looks fundamentally different from the world after. Species lists change, but more importantly, the way communities function changes. The rules don't change, but which species play which roles does. And the transition takes longer than human civilization has existed. We're now watching this process begin in real time. Ocean dead zones are expanding. Areas where oxygen depletion kills fish and invertebrates, creating underwater deserts. Coral reefs are bleaching and dying, taking their associated species with them. Overfishing removes top predators and key herbivores, causing trophic cascades. Nutrient runoff from agriculture creates algal blooms that crash when the algae die and decompose, depleting oxygen. These aren't hypothetical future scenarios. They're measured, documented, ongoing changes. The principles causing them are the same ones that caused Cambrian anoxic events. The difference is speed. Natural events played out over thousands of years. We're causing similar stress in decades. Ecosystems adapted to gradual change are facing rapid shock. The Cambrian ecosystems operated under rules that still apply. Energy pyramids, trophic cascades, nutrient cycling, competitive exclusion, ecosystem engineering. These aren't old principles that evolution replaced. They're fundamental constraints that every ecosystem must obey. Break them, and the system collapses. The Cambrian proves this. We see the collapses in the rock record, the recovery timescales, the species that vanished forever. Modern ecosystems are equally vulnerable to the same violations. The difference is we're causing multiple violations simultaneously, removing species, disrupting nutrient cycles, changing temperature and chemistry, fragmenting habitats. Each principle broken makes the others harder to maintain. The Cambrian shows us that ecosystem collapse is possible. What we're doing suggests it's likely. Evolution takes millions of years to rebuild complexity after crashes. This isn't pessimism, it's the fossil record speaking clearly. After mass extinctions, life rebounds eventually. New species evolve to fill empty niches. Ecosystems reorganize. Biodiversity can recover or even exceed previous levels. But the timescale is geological. Humans evolved over the past few million years. Civilization emerged in the last 10,000. Industrial society spans 3 centuries. We're collapsing ecosystems that will take thousands of times longer to recover than we've existed as a species. The Earth will be fine, life will persist. The question is whether complex ecosystems, including the ones we depend on, will survive intact, and whether the recovery happens on timescales relevant to human survival. The Cambrian established rules that life has followed for 540 million years. Those rules built ecosystems of astonishing complexity and resilience. They survived multiple mass extinctions, climate changes, and continental rearrangements. But resilience isn't invincibility. Every system has breaking points. The Cambrian shows us what happens when those points are reached. Collapse, extinction, millions of years of recovery, and a fundamentally different world emerging from the ruins. We're now testing those breaking points globally, simultaneously, faster than any natural catastrophe in Earth's history. The ecosystems we're collapsing follow the same principles that Cambrian ecosystems did. The difference is Cambrian life had millions of years to recover before the next crisis. We're not giving modern ecosystems that luxury. We're creating the crisis, living through it, and will face the consequences within our lifetimes. The Cambrian can't tell us if we'll survive, but it can tell us exactly what we're risking. Cambrian ecosystems weren't ancient curiosities. They're the operating system life still runs on. Break the system, crash the program, In our next episode, the finale, we'll synthesize everything. What does the Cambrian mean for us today? What lessons can 540 million years teach about survival, extinction, and the future? The Cambrian explosion created the modern world. What we do next determines how long that world lasts. This is HistoPrimordia, where history comes alive. Thanks for watching. Subscribe now and join us for the next episode story.